Well, good morning. It's nice to be back among you. It's been a few years since I've had the opportunity to be at a CRCPD meeting. And so as Lynn said, what we want to do this morning, first off, is we want to talk about the dose indices that we've traditionally had for CT, but we also want to talk about a new dose indice that you may not be that familiar with. Just as some acknowledgments, hopefully you know some of these folks on this list. That list alone is a pretty august list of medical physicists that I hope you've had an opportunity to work with at least one of them. So I'm going to say a few words about image gently. I want to talk about the effect of patient size on CT dose indices and why that's important. And I'm going to talk about the shortcomings of our traditional dose indices. CTDI, CTDI 100, CTDI-W, CTDI-Vol, DLP, and effective dose. I'm going to pick on all of them this morning. I'm going to talk about the difference between displayed and measured CTDI-Vol, which generates a clinical dilemma for us, and we'll talk about that. And the solution to that really is a new dose indice that was developed in 2011, and it's called SSDE. It stands for Size-Specific Dose Estimate. So we'll talk about that in some detail. So you all know, I'm sure by now, a little bit about Image Gently. Simply, its mission is, through advocacy, to improve the safe and effective imaging care of children worldwide. The safe relates to radiation protection. The effective relates to image quality. We can't do one without the other because they're balanced against one another. Currently, Image Gently represents about 85 different healthcare organizations and agencies around the world, and we believe that that represents about 1 million medical workers worldwide. Image Gently is always going to present the quote-unquote risk of radiation in a positive message. You will never see this kind of statement from Image Gently. Resulting dose to population will lead to higher cancer rates, accounting for as many as 2% of all cancers in the US. That is not a positive message. That is not science. That is not truth. That is a prediction based on literally hundreds of assumptions that are associated with the linear model of risk. And if you see anything like this, it's not coming from Image Gently. It's coming from somebody else. And it's interesting. Image Gently has been accused by some folks of actually contributing to that kind of thing. So we want to enroll key organizations. We want to increase awareness by education and by advocating. And we want to change practice in less than 17 years. Well, what's the significance of 17 years? There was a study done not too long ago where they determined that the average time it takes for a breakthrough change to actually get into the clinic and have an impact is 17 years. And we at Image Gently feel that's just a little too long. So we're trying to shorten that time period. The founding organizations was the Society for Pediatric Radiology and the American College of Radiology, which of course represents the radiologists and the physicians, and then the American Society of Radiologic Technologists obviously represents the technologists, and then the American Association of Physicists in Medicine represents the physicists. We really believe that things work best when these three groups of individuals work together as a team. You take one of these arrows away and you've got a big hole in the equation and you don't have all the information that needs to go into clinical decisions involved. This is a slide that was put together a few years ago by Eric Hall, just to remind us again. On the ordinate here, He's got the attributable lifetime risk from receiving 1 sievert of dose. Obviously, 1 sievert of dose is quite a bit of dose. And the average here is about 5 to 6% over your lifetime. If we look at just the first decade, it's 13 to 15%. If I look at middle age, it's down to 2 to 3%. It's about the only thing I can do better than my kids and my grandkids. And as a result of that, we assume that children are 3 to 5 times more sensitive. Now, I say assume because there's been data recently published that shows that this elevated level of sensitivity is true for some carcinogens, but not all. So we keep learning more as time goes on. The effect of patient size on the displayed CTDI vol and DLP is important. This is the size of a neonate. Here's a 1-year-old, a 5-year-old, an adult, and a large adult. And then this is a scale drawing, and it turns out that that short bar is equal to 4 centimeters. And what's significant about 4 centimeters? Well, 4 centimeters is roughly a half value layer in tissue if I use 120 kVp and typical filtration that CT scanners use. So every time I change the thickness of the patient 4 centimeters, I need to double the MAS to deliver the same amount of radiation to the detector and keep the noise characteristics in the image the same, provided I'm not changing the kV. So what about the real world? Well, here's our patient, and we're going to use a fan beam width in the Z direction, in this case, of 10 millimeters. And if we had a nice cooperative world, that area of the patient that would be irradiated is represented by this nice, tidy, rectangular box in white. But because we have scatter radiation, we have dose tails outside the box, and obviously we have a rounded peak to what we call our dose profile. And so we call that the peak dose. So radiation distribution crosses the image volume. If I use a 10 millimeter beam width in the Z direction, more than 10 millimeters of patient tissue is going to receive some radiation. So we call that the dose profile. And fundamentally, what's CTDI? Well, CTDI is the integral under the radiation dose profile along the Z-axis. Well, integral is just a mathematical way of saying we're measuring the area underneath that profile. And that's from a single axial scan with a width NT, which is the half width at the full width at half maximum. And what's NT? Well, T is the dimension of an individual detector in the Z direction of the CT scanner, and N is the number of detectors in the Z direction that I'm actually using as I'm acquiring the data. So that's CTDI. Well, we know that if we do an axial scan, we're going to do the scan in a manner that I have dose profiles lined up side by side like this. And we notice from this that I get a contribution to my central profile from the dose tails on either side. And as a result of that, the total dose is equal to this peak dose plus all the contributions from the tails. And so my CTDI 100 is the average value of the overall dose profile that comes from the single individual profiles. So that's fundamentally your definition of CTDI 100. Well, We all know about CTDIW. What is it? Well, we're weighting the two traditional CTDI measurements, the one that's a centimeter below the surface of the phantom and the one that's at the center of the phantom. And we're taking a third of the central reading and 2/3 of the reading 1 centimeter deep. And if we do the math, where I have 100 units of dose at the surface and 50 in the center, I'm going to come up with 83 milligray. Well, 83 milligray really occurs in a ring that's about this depth in the patient. And obviously those rings, as you go to the center, the dose gets smaller. You go to the surface, it gets larger. And basically it's an average dose over the entire cross-section. Well, that's CTDIW. How do we get to CTDI vol? Well, CTDI vol is simply CTDIW divided by the pitch. And the pitch, of course, is dealing with how rapidly our table is moving the patient's anatomy through the gantry. If I increase my pitch, my anatomy is in the gantry for a shorter period of time, and so my CTDI vol is going to decrease relative to CTDIW, and vice versa. Okay, so what CTDI vol really does is it addresses the dose when the table's in motion. So what's dose length product? Another dose indice. It's simply the CTDI vol times the scan length. The scan length is the point in the patient from where the scan starts to where the scan ends. We irradiate a volume of tissue, and the scan length gives us the length of the patient's body that's actually receiving direct irradiation. Now, DLP, however, is DLP a dose to the patient? No, it's dose to a phantom, because CTDI vol is dose to a phantom. CTDI vol has nothing to do with patient dose, absolutely nothing. And so neither does DLP. So what does it represent? Well, it represents the energy that's transferred to the phantom, not to the patient. So DLP is not a patient dose index because CTDI vol isn't. So why do we use CTDI vol and DLP as an indicator of patient dose? Well, for about 30 years, it was all we had. But that 30-year reign is over. We have something better today. We'll talk about it in a little bit. So I've already said that SSDE is a better indicator of patient dose, so should we substitute SSDE for CTDI vol in the DLP formula and calculate the CDELP instead of DLP? Well, we can, and if we do that, we'll get a better indication of what the actual energy that was transferred to the patient was. All right, well, why was DLP created to begin with? What purpose did it serve? Well, if I have a patient and I do 10 axial scans with a pitch of 1, so I don't gap any of the anatomy, and let's assume the CTDI vol is 20 milligray from 10 1 centimeter slices. Well, in a second case, I'm going to double the number of slices. Does that change the CTDI vol? How many think that changes the CTDI vol? No, it doesn't. CTDI vol stays the same. But I don't think you'd get much of an argument if you started a debate of whether or not the second case here maybe carries more risk to the patient than the first. And so that's where DLP comes in. We now have the same situation here, and my DLP with only 10 slices is 200 milligray centimeters. And down here, my CTDI vol again has not changed, but my DLP is doubled because my scan length is doubled. So that's the role that DLP typically plays clinically, but again, it does not represent patient dose. Well, just as a quick review, how do we determine CTDI vol? Well, we take, the standard CTDI vol phantom that's shown here, and we take a pencil chamber and we put it in the central hole and we plug the surface hole, we make a measurement, and then we repeat that. You've all seen this. I'm sure you're familiar with the CTDI phantom. The one on the left here is the body phantom. The one on the right in the gantry is the head phantom. Oh, and by the way, in pediatrics, where should you put the phantom when you measure for pediatric purposes? Where should you put the 16 centimeter phantom? In head holder or on the table? Head holder or table? Table. Why? You can't put an infant in a head holder. Their body is precariously supported by the junction between the head holder and the actual table. So little children, when they're scanned, are all on the tabletop, and so that's where you should put the phantom. So let's do a little experiment, which I think clarifies some of the issues for us. Let's take the 3 CTDI phantoms, and the third one is 10 centimeter diameter instead of only 16 and 32. And let's use those, and we're going to use the identical KV, the same MA, same rotation time, and we're also going to use the same bow tie filter. So the output of the CT scanner is the same. Now, why do I have that highlighted? Well, some scanners change the bow tie filter as you change the field of view selection. So you got to make sure that you don't do that when you do this experiment. So here's our 3 phantoms. Here's the results of our measurements. And we calculate 47 milligray for 10 centimeters, 37 milligray for 16 millimeters, and 18 milligray for the body phantom. Does that seem kind of odd? We used exactly the same technique for each of the 3 cases. Notice that there's a 2.6 times difference between the measured CTDI vol for the 32 centimeter phantom compared to the 10 centimeter phantom, when the radiation output of the X-ray machine was identical. So what's going on? Well, with the larger phantom, the outlying parts of the phantom attenuate the X-rays before they get to the center. And as a result of that, it's the patient's tissue, peripheral tissues, provide some radiation protection for the centrally located tissues. Okay, so what is CTDI vol? I've said it's not a patient dose. Why was it developed? Well, it was simply developed to give us a standard method to estimate and compare the radiation output of 2 different CT scanners to the same phantom. That's helpful to know if you're buying a new CT scanner. But that was the only purpose of CTDI vol. Now, if the fan beam is relatively small, we're not going to have the issues that we have in the clinical situation, which is addressed in AAPM task group TG111. Those of you that are not familiar with that, that group has identified that all of our CTDI vol measurements are too high or too low with respect to reality. Too high or too low? How many too high? How many too low? You don't know, I guess. Well, what do those tails do? They contribute to dose. Now, how long are those tails in an adult abdomen? If I'm in the center of the abdomen, I've got tails going both directions. That's going to elevate the CTDI valve. And they spread for 35 centimeters in both directions from the center. So let's just assume I'm doing an abdomen and the belly button of the patient is in the center of the scan length. So I have to go 35 centimeters both directions from the umbilical and collect all those tails to have an accurate dose indication. Can I do that? Well, what do I use to make a CTDI valve measurement? I use a pencil chamber. How long is it? Yeah, somebody said, it's this long. Well, that's 100 millimeters or 10 centimeters. I'd need a pencil chamber 70 centimeters long to capture all the dose. So our CTDI valve measurements today are too low. They do not reflect reality. Okay? And that's why TG111 was started. There's TG200, which is developing a standardized phantom to make these measurements. And the idea is that we won't make those measurements in the field because nobody wants to carry a 70 centimeter phantom because it weighs about 200 pounds. Okay? So the idea is we'll ask the manufacturers to make careful measurements in the factory, and they will give us correction factors for their model scanner to apply to our measurements in the field. Yes?
So the lateral scattering, do you account for the attenuation of tissue as the beam penetrating laterally deeper or superior defined? Or simply this beam is scattered homogeneously throughout that 10 centimeters?
Well,
We're capturing this. If you have a question, please use the microphone because we're capturing this session.
come to the microphone.
Let me try to capture my question. And that is, would you, based on the calculations, would you account for the scattering laterally to the side, or you simply?
You're accounting for the scattering in the Z direction.
Yeah, you do.
In the
Now,
Z
it's not
direction.
so much of a
The tails are in the Z direction,
right.
along the central axis of the patient.
So, but the body is not homogeneous in terms of absorbing the scattered radiation. So, do you account for that? Because the tail will definitely drop off, possibly logarithmically, to the side.
Well,
So it's not-
again, we don't have any phantom that really accounts for exactly what happens in the patient's body.
Right, so-
Because the phantom's uniform, but it is
Right.
70 centimeters long so that I capture all the tails.
Yeah, but every slice that is moving away from the central axis,
Yeah.
you get a lower dose logarithmically.
Well,
Right.
well, the other thing is you don't use a pencil chamber, you use a point chamber.
Yeah.
We can talk about it offline.
Okay, thank you very much.
Yeah. Okay, so our current CTDI measurements are low due to the failure to capture all the scatter. So if you don't remember anything else that I said this morning, remember this. CTDI valve does not represent what? Patient dose. Okay, somebody's awake. Great. Okay, now let's finish our experiment. Remember, we irradiated these three phantoms and we measured the CTDI valve values that you see at the top of the slide. What's the scanner going to display when I do this experiment? Well, if it uses the 16 centimeter phantom, it's going to display 37 milligray in all three cases. What's the definition of CTDI valve? It's the dose given to a phantom. That phantom doesn't change. So if it uses the 16 centimeter phantom for its calculations, you're going to get 37 milligray in all three cases. If it uses the 32 centimeter phantom for its calculations, you're going to get 18. And we know that's not the truth. The truth is across the top here. Okay? Now think of these three phantoms as representing three different sized patients. Same thing happens. The doses are dramatically different if the patient size is different, but the scanner is going to give you exactly the same number. CTDI vol on scanners today doesn't in any way follow the size of the patient. It's dosed to a phantom, and that phantom is fixed. CTDI vol is not patient dose. Now, what's wrong if the scanner uses the 32 centimeter phantom and I do an abdominal scan on a baby? Well, the baby's represented by the 10 centimeter phantom. What's the dose to the baby? 47 milligray. What does the scanner tell me? 18 milligray. Dose to the baby was 2.5 times greater the dose of represented by the CTDI vol. What happens? The radiologist or the technologist that thinks CTDI vol is patient dose says, great, my dose is really low. It's only 18 milligray. It gives them a false sense of security. So we've got a little patient, we've got a large patient. If we use the same technique, the scanner is going to tell us the CTDI vol was the same. If we use the 16 centimeter phantom, the adult dose is going to be greater. If we use the 32 centimeter phantom, the adult and the pediatric dose will be underestimated. And what are we doing with all this data? What are we doing with CTDI vol? We're propagating it, and where are we putting it? In the PACS machine for perpetuity. Patient dose. And who is our leader in this? I can't blame Melissa because she's not, she doesn't sit in the government of California, but California has mandated that the CTDI vol has to go into PACS and into the patient medical record, so we know their dose. We don't know their dose. Okay? So what does the Joint Commission do? Well, if it's good enough for California, it's good enough for the entire country. I'm starting to sound like Trump. All right, you're familiar with these phantoms. You may not be familiar with the 10 centimeter phantom, which is in the center here. This is a nested phantom, and the different pieces are taken out. There's a ruler there, 18-inch ruler on the table. Of course, the pencil chamber is there too. We have better phantoms than the CTDI phantoms to represent the patient attenuation. The small phantom here is a newborn chest. The large phantom on the right is an averaged adult. And you notice there's lung tissue in there and there's spine tissue. Those two different areas are actually attenuate the radiation beam similarly to what happens in actual anatomy. But even our anthropomorphic phantoms are not as good as they should be. And of course, we can't use our best representation of the patient's body for research purposes. Okay, so see how we're doing. CTDI vol is measured with a point small volume ionization chamber, represents the radiation dose to the patient, estimates and compares the radiation output of two different CT scanners to the same phantom, can be measured in a CTDI phantom with a single measurement, and is measured with a pencil ionization chamber with a length of 90 millimeters, which is the correct answer. Well, I see one right answer. Hold your hand up with the right answer. Yeah, okay, it's number 3. okay? All right, I've disparaged the other dose indices, so I need to finish up and disparage effective dose. Okay, what is effective dose? Well, it's the whole body uniform radiation dose that reflects the same risk to the patient as that larger radiation dose that we deliver to the fraction of the patient's body during the actual scan. So my effective dose is always going to be greater than my CTDI vol or my SSDE, okay? And how do I calculate effective dose? Well, I have these magical constants that I multiply times the DLP to give me my effective dose. And of course, the K factor, or that constant, is a function of patient size, the body region imaged, and of course the CTDI phantom that the scanner assumes, 16 or 32 centimeters, is going to determine the value of the DLP. Now, why don't I like effective dose? Well, we'll save that for a minute. So we already talked about CDELP. CDELP is just substituting SSDE for CTDI vol in the DLP formula. And that's a reasonable thing to do, and you'll get a better answer of the energy transferred. Can I do that for effective dose? Should I take the SSDE value and use it instead of CTDI vol to get a better estimate of effective dose? And the answer to that is no. And why is that? Well, here's our equation for calculating effective dose. And if you think about it, our effective dose, does it change because, or is it inaccurate because CTDI vol is inaccurate? And the answer is no. Because what we actually did to develop the K factors was we measured the effective dose in phantoms. We took a look at what the DLP was and said, what do we have to make the constant so that I multiply the constant times the DLP, I get the right effective dose? So I'd have to come up with new K factors if I was going to use CDELP instead of DLP to calculate effective dose. So effective dose is not changed by using SSDE, and obviously DLP is changed if we use SSDE, so the K would have to change. Now, can I use effective dose to estimate an individual patient's radiation dose? Yes or no? No. Why? It's not defined. Effective dose is not defined for individual patients. So why do you see it in the literature? Why can you find multiple papers in the literature where this has been done, and it's been accepted, and it's been published? I thought the literature was the truth. You got to look at literature with a careful eye. The reviewers didn't do a very good job. Today, most journals will not accept a CT paper on dose if it expresses dose and effective dose because it's not defined for an individual patient. Can I use it to estimate organ doses? No. What can I use it for? Well, it was originally defined to address radiation protection concerns of occupationally exposed workers. It had nothing to do with patients. Well, today they've softened that, and now we're allowed to use effective dose to compare the biological effects between, for instance, two different diagnostic exams of different types. But that's to a group of patients, not an individual patient. If you want to learn more about the positives and the negatives of effective dose, and you'll have all this available because you're going to get these slides, here's 3 or 4 references that you can go to. So effective dose compares biological effects between diagnostic exams of different types. Should be substituted for CTDI vol when calculating E-dose with K-factors. Can be used to estimate an individual patient's radiation dose. Can be used to estimate organ doses. Is defined for individual patients, which is the correct answer. Number one. Okay. All right, so that gets me finally to the dose index that I want to talk about. And as I've said, it's called size-specific dose estimate. The acronym is SSDE. Why does it have estimate in the name? Why doesn't it just say size-specific dose? Why does it have estimate in the name? Do medical physicists measure dose? Yes or no? Do medical physicists measure dose, typically? No. What do they measure? Exposure or air karma. How do we get to dose? We take the exposure or air karma, which is the ability of the machine to produce radiation, and we convert that to dose. Dose is always an estimate. We never know unequivocally exactly what the dose was. Now you notice here on the title that this says that SSDE can be applied in pediatric and adult body CT examinations. Body means thorax, abdomen, and pelvis. And notice it says pediatric and adult. There's a lot of adults that are larger than the standard-sized adult that you should use SSDE to correct what the dose would be for those large patients also. So what does the report intend to do? It addresses it does not address correction factors for heads. We're working on that today. Hopefully we'll have that in a year. It doesn't correct for the small doses from the scan projection images, or commonly referred to as scouts, but that dose is less than 1% typically of the total dose the patient received. It doesn't correct for the variation in attenuation of the thorax versus the abdomen, which is about 5 to 7%. It doesn't correct for the small variation in the pre and post contrast scans, which doesn't really matter because you're not supposed to do those anymore. You're supposed to do one or the other and be done with it. Okay, so really what is SSDE? Well, it estimates the peak soft tissue dose. Notice I said soft tissue of the patient at the center of the scan length. So it's kind of like CTDI 100, except it now accounts for changes in patient thickness. Now, again, it's soft tissue dose. What do we know about the spine? If I've got 20 milligrams of soft tissue dose in an abdominal scan, what's the dose to the spine? Anybody? How much more is the dose to the spine? It's about 4 times greater. So if I have 20 milligray to the soft tissue, I've got about 80 milligray to the bone. So again, SSDE is for soft tissue, not for bone. Now, it uses the average scan radiation output, CTDI vol, okay, and we correct for that. Now, the people that did TG111, I won't actually name the one culprit, but the one culprit has said to me, well, SSDE is crap because CTDI vol is crap. And if you start with crap, you wind up with crap. Well, what he's not acknowledging is that when we get around to correcting CTDI vol, that will also automatically correct SSDE. Because the conversion factor that we use to get to SSDE today will not change because in the future we're accurately going to account for those dose tails. So don't sit there and think, well, as soon as we change the CTDI vol, this SSDE stuff isn't going to apply anymore. It still will. Now, the question comes, can I use SSDE as a useful approximation of organ dose? You know, organ dose is the holy grail, especially among all the people, all the researchers that are developing these huge computer libraries of organ doses. Now, I don't know as a medical physicist what I'm going to do with those organ doses, but it doesn't really matter because by the time they come around, they'll be off in the sunset. But anyway, the question is, here's my organ. Is SSDE a good approximation of the dose to that organ? What do you think? No, it isn't. Why? Well, the CTDI vol, remember, was the average dose that occurs about that distance from the center of the patient. So that small organ is going to get less organ dose than what SSDE suggests. How about that one? That organ is going to get more dose than what SSDE would suggest. And how about that one? That one, its organ dose is approximated by SSDE. Now notice I said approximated. Okay? How about that organ, which represents the liver and the abdomen? How about that? Is the CTDI vol, or I'm sorry, is the SSDE a good approximation of the organ dose to the liver on average? Yes, it is, because the organ basically spans from the surface of the patient all the way to the center. And again, the CTDI vol that we used was to come up with an average dose as we move radially within the patient's body. And just, this is an abdomen, this is the liver, and this is the aorta, and so based upon what I said, you know, yes, we can estimate the dose to large organs, but we need to be more careful to the small organs, like here's the aorta, and, you know, obviously that's not a good representation. So what did TG204 really do? Well, we took data from 4 independent sources. 2 of the sources did physical measurements in phantoms, and 2 of the sources did Monte Carlo simulations. So we all worked independently. We really didn't know what each one of us was doing, and we took all our data and we put it all together in one plot, and lo and behold, there's a reasonable fit of the data. And on the ordinate here, you have the number, the normalized dose coefficient, which becomes the conversion factor that's published in TG204. And down here on the abscissa, you have the effective diameter. And I'll define the effective diameter in a minute, but it's basically the size of the patient. You notice my R squared is 0.94, so that means I've got a pretty reasonable fit to my data. And this is for the 32 centimeter phantom at 120 kV. All right, when I say 32 centimeter phantom, that's the phantom that the manufacturer is using to make their estimates of CTDI vol. Here's the same thing for the 16 centimeter phantom at 120 kV. Now, if I go back for a minute, you notice that my correction factors for the small patients are as great as 2.6. Where did we see 2.6 earlier? Remember, we saw that in our little experiment. It was the difference in dose between the 10 centimeter phantom and the 32 centimeter phantom when I used exactly the same radiographic technique. If I go to the 16 centimeter phantom, notice that my correction factor never gets bigger than 1.2. So the 16 centimeter phantom's not a horrible representation of dose to a small child, but none of the manufacturers anymore are going to present CTDI vols for pediatric abdomens based upon the 16 centimeter phantom because the IEC recently changed the rules so that they have to always use the 32 centimeter phantom for bodies. So then you say to me, well, Keith, that's great, works for 120 kV, but all the sites I go to now, when they do pediatrics, they use 80 and 100 kV. What do we do about that? Well, these two curves address that. One's for 120 kV, and the other one's for 80 and 100 and 140 kV. And you'll notice the two curves are pretty identical to one another. And in fact, there's a 5% difference overall. There's a 3% difference between the 1-year-old at 15 centimeters and the adult at 32 centimeters. I can live with that. Okay? I never said SSDE was accurate to 0% error. It's only plus or minus 20. It's an estimate because remember, we're identifying a dose. It's not exact. Now, then when we originally tried to get the thing published, some of the graybeards in the AAPM said, you can't say this is for the body. You can only say it's for the abdomen and the pelvis. You can't say it's for the chest. So we went out in the literature and we found some data that was put together by Huda and others. And basically, there's a 16% difference here at 12 centimeters between the chest and the abdomen. It's only 7% at 17 centimeters. And it's less than 3% for anything above 17 centimeters. And we basically said that SSDE is only accurate to plus or minus 20%. So finally, the naysayers relented and said, okay, you can say it's for the entire body. Now, what's effective diameter? The effective diameter is the diameter of a circle that has the same area as the elliptical shape of the axial scan of the patient. So, I have an AP and a lateral dimension over here, and I can calculate my diameter of my effective diameter of the circle that has the same area. Now, what if I don't know the size of the patient, but I know the patient's age? Can I use age? Well, I can. This is actually in the report. It gives you effective diameters as a function of age. And there's a table in here to make the corrections, but I saw some people shaking their heads no, and they're correct. You really shouldn't do this. This is a plot of the lateral dimension of the abdomen where the age of the patient is on the abscissa and the physical measured size is on the ordinate. Okay, now you notice, I hope, that the same age patient has variation. The 3-year-olds here, by this blue vertical line, are anywhere from 10 to 15 centimeters in size. The 6-year-olds up here are 11 to 22 centimeters, and the 18-year-olds are 15 to 30 centimeters. So one of the things you notice is that for the same age, there's a factor of 2 difference between the largest and the smallest patient. But look at this. My largest 3-year-old is the same size as my smallest 18-year-old. So I can't use age with any kind of accuracy. And that's why Image Gently has promoted the idea that you really should use the physical dimension of the patient. Well, how do we determine patient size? Well, after the scan, it's easy. If you take the projection scan, you can draw a line across the region of the body you're interested in, and the scanner will tell you the size. You have to be careful in this case that the patient is centered vertically in the gantry, because if it's not, you're going to get magnification error. After the actual scan, I can measure both the AP and the lateral dimension on the transverse image. The beauty of the projection scan data is I have that before I do the helical acquisition. And as a result of that, I can use that to manage patient dose, which we'll talk about at 11 o'clock. before I do the actual scan. The AP and the lateral dimension both I won't know until after the actual scanning is finished. So, you know, how do you get that size beforehand then if you don't have the projection scan? Well, how many of you in here have heard of calipers? There's some of you that have gray hair. You know what calipers are. Okay, well, this is just a picture of taking the size of the AP dimension of the abdomen of the patient. We don't recommend that in CT. We recommend that you do the lateral dimension because all the tabletops are curved, and it's much easier to drop a set of calipers in the lateral dimension on the supine patient than the AP. You don't have to get quite so personal with the patient to do that. Please be careful if you work with SSDE. You absolutely have to know whether or not the CTDI vol on the scanner was calculated based on the 16 or the 32 centimeter phantom. And unfortunately, there's no standard. Some manufacturers change between adult and pediatrics, some don't. Some change as a function of the scan field of view. Some change in the same model based on the year of manufacturer or even the software level. So don't make any assumptions, talk to the manufacturer. I've already alluded to the fact that we believe the accuracy of the SSDE is plus or minus 20%. So again, that calculation of the conversion factor times CTDI vol is an estimate of patient dose. So since it's an estimate, demonstrate that you know that when you talk about SSDE. How do you demonstrate that? Well, if the SSDE is greater than 5 milligray, the report recommends that you use only integers to represent the SSDE, because 20% of 5 milligray is 1 milligray. So you only need to use integers, because that's all you know. If the SSDE is less than 5 milligray, it's okay to use 1 decimal point to represent SSDE. Don't want to see an SSDE that says 7.6893 milligray. That's, you know, if you do that, all you're doing is demonstrating the fact that you don't realize that it's just an estimate. Now let's look at a couple quick calculations. Here's my axial scan. I know my lateral dimension, it's 12.3 centimeters. I go to the table for lateral. I go down to 12 centimeters. I know I used a 32 centimeter CTDI vol phantom to calculate CTDI vol, so I picked that table in the report. My displayed CTDI vol is 5.4 milligray, and there's my calculation. I get 13 milligray SSDE. Notice I didn't say 13.4. Okay, I said just 13. All right. Now, that's if I know just the lateral dimension. Well, let's say it's after the scan and I know both. Well, both is 22 centimeters, so I go to a different table. Again, I'm assuming the 32 centimeter phantom. And so since it's the 30 centimeter phantom again, the CTDI vol is the same. I go to this table and I look up lateral AP and I look up 22, and lo and behold, I get a correction factor of 2.5 again, and voila, I got the same answer. That's a good thing, because it's the same scan. Okay? Now, what if the manufacturer is using the 16 centimeter phantom instead? Well, the patient sizes haven't changed, but my displayed CTDI vol has. It's no longer 5.4, it's 10.8. So I go to a different table and I look up the lateral and the AP, and I go down to 22, and now my correction factor is only 1.24, but that multiplied times 10.8 again gives me 13 milligray. So everything hangs together in TG204. There also are apps out there that have been developed that allow you can put a little app on the PC next to your CT scanner that lets you plug in the information that's needed to do these calculations for you. So SSDE is a calculation that has an estimated error of 10%, accounts for both radiation output of the scanner and patient size, cannot be estimated until after the CT exam is completed, is more accurate if patient size is estimated based on the patient's age, and should not be used for CT examinations of the thorax. Which one's true? Number 2, it accounts for both the radiation output of the scanner and the patient size. If the patient size changes, SSDE will change, even if the technique factors are unchanged. If the patient size doesn't change, but the technique factor is changed, CTDI vol will change and SSDE will change. Okay, so it accounts for both. What's the future of SSDE? Is there a future? Well, those of us that developed it from the very beginning thought it was only an interim solution until someday we had organ doses, but we don't know when that's going to be. So the IEC is the international organization that sets the standards that all CT imagers have to meet to be sold internationally. And there's no CT manufacturer today anymore that doesn't want to sell their equipment internationally. So we're currently on the IEC developing a standard that in the future is going to require the CT scanners to calculate and display the SSDE in addition to the CTDI vol. It's going to display the SSDE after the projection scan and update it at the end of the exam so that the first displayed SSDE can be used, as we'll talk about at 11 o'clock, to manage the dose to your pediatric patients. The other beauty of having the manufacturers do the calculations is that they know how the body actually attenuated the X-ray beam during the projection scan. And they use that data to drive their automatic exposure control capability. Since they know how the attenuation between the chest and the abdomen differ, for instance, because the chest has a lot of air in it, once the manufacturers start displaying SSDE, the results will be more accurate than what we can do today by using the correction factors in the report, because there's no way we know how the attenuation is differing between two different regions of the body. And we'll know that once the manufacturers get involved. So estimating and managing a patient's CT dose as a function of their size is facilitated by using SSDE, provided you know the CTDI vol, which phantom was used by the manufacturer to represent that, and you know the patient's size. Thank you. Good. Any questions?
Maybe you're going to talk about this at 11 o'clock, but we've gone to large bore CTs. Is the measurement using phantoms, all that, is that the same, or has that changed?
No, it's the same, and we can talk about that.
Okay.
At 11 o'clock. Other questions? Okay, it's great to know that you guys are all experts on SSDE now.